Hi everyone. My name is Runbang Tang. I recently graduated from uh, University of Washington, and I'm from Professor Ratner's lab. Today, my topic is smart solvent, molecular polymers for indoxyl sulfate. Um, okay. So the indoxyl sulfate is a very common toxins in uh, heme blood, and during hemodialysis, unlike urea, which are free species in blood, so it can be effectively removed through dialysis. But in terms of indoxyl sulfate, which 90% of indoxyl sulfate were protein bound, therefore, during normal hemodialysis, it cannot be effectively removed. As a result, you can see graduation of the chronic kidney disease, the level of indoxyl sulfate is increasing in blood serum, and the elevated level of indoxyl sulfate actually causes a lot of problem. It can advance the kidney disease to a further stage, and also it can cause a lot of cardiovascular disease, and also it can cause bone issues. Therefore, it's very important to develop some materials that can effectively remove indoxyl sulfate in hemodialysis. And in our group, we come up with the idea to use molecularly imprinted polymers to do that. Molecularly imprinted polymers works pretty much like the antibody. So it has a cavity which not only has the shape of the target molecule, but also has specific interaction with the molecule, as you can see here. So the end, therefore, in order to mimic the binding between the antibody and the target molecule, we have to design monomers that has specific interactions towards the target molecule, which in our case would be the indoxyl sulfate. Looking at the structure of the indoxyl sulfate, we can see that indoxyl sulfate has a negative charge, which can form electrostatic interaction, and it has some oxygen items and nitrogen items which can form hydrogen bonding, and also it has a aromatic ring, indole ring, which can form pi stacking. Therefore, we design some monomers that has the electrostatic interaction, some monomers that has the hydrogen bonding, and some monomers which can form pi stacking. With that designing principles, we synthesize a bunch of polymers. And the first experiment we did is to test the capacity of those polymers to see how much the polymers we synthesized is able to absorb the indoxyl sulfate in the environment. As we can see here, when we only use one kind of interaction, no matter it's electrostatic interaction or hydrogen bonding or pi stacking, the capacity is pretty low. But when we combine two or more interactions, such as hydrogen bonding or together with electrostatic interaction, we can have some polymers that has very high capacity. Since we already got some polymers that has high capacity, the next property we want to confirm is that whether this polymers is specific to the indoxyl sulfate, meaning that the polymers only binds to the indoxyl sulfate without binding to some other molecules similar in structure. So we did the specificity studies where we compare the binding behaviors towards 4 different kinds of molecules. 2 of them are toxins. The other 2 of them are amino acids, which are actually nutrients. Are benign molecules. As we can see, the molecular imprint polymers we synthesize have very high capacity binding to indoxyl sulfate. And surprisingly, it also binds to another toxin, which is picresyl sulfate, which are very similar in structure to indoxyl sulfate. But they didn't bind to the nutrients, no matter it's glutamic acid or tryptophan. Therefore, we confirm that our polymers the binding are quite specific to the target molecules. And also we find out that the molecular imprint polymers we synthesize, although we design it to absorb indoxyl sulfate, it can also remove the picresyl sulfate at the same time. With these studies, we can conclude that we successfully synthesize some polymers that are able to absorb indoxyl sulfate, and also we find out that the binding cavity or the molecule recognition is a combination of shape recognition, hydrogen bonding, as well as charge interaction. And finally, we found that the polymers we synthesized can specifically bind to indoxyl sulfate, but it will not bind to nutrients like glutamic acid or tryptophan, although they were similar in structure. So I'd like to thank my advisor, Professor Ratner, to provide funding for my research, and also I would like to thank all my group students in my group to help me with the ideas and the experiments. And I'm happy to take questions.
Thanks.